Good day. Welcome to How to Assess and Manage Neuroinflammation to Optimize Cognitive Function. My name's Andrea Gruszecki. I'm a client consultant in the Scientific Support Department of Doctors Data. Today we're going to review the evaluation of biogenic amine and neurotransmitter metabolism and its effects on the dysfunctions in synthesis or metabolism in the nervous system. We'll review how toxic exposures, inheritance, and nutrition can all affect enzyme functions and neurotransmission. We'll review strategies for nutritional support of neurotransmitter synthesis and metabolism as outlined in the scientific literature. And we'll review some strategies to diminish oxidative stress and neuroinflammation in our patients. Neurotransmitters are endogenous substances that act as chemical messengers by transmitting signals from a neuron to a target cell. The communication of information between neurons is accomplished by movement of neurotransmitters across a small gap between neurons called a synapse. Prior to their release into the synaptic cleft, neurotransmitters are stored in secretory vesicles near the plasma membrane on the nerve's axon terminal. The chemicals are released into a nerve synapse from a presynaptic neuron. They convert electrical signal from the neuron into chemical signals to cross the synapse, and the chemicals are then picked up by specialized receptors on the receiving postsynaptic neurons. Receptor stimulation can result in nerve firing, which is an action potential, or can activate secondary messengers. The activity of a nerve cell is determined by the balance of excitatory and inhibitory signals that it receives. And neurotransmitters are generally classified into two main categories, either excitatory or inhibitory. Excitatory neurotransmitters increase the likelihood that a neuron will fire an action potential. Major excitatory neurotransmitters include glutamate, epinephrine, and norepinephrine. Too much excitation can lead to restlessness, irritability, insomnia, and even seizures. Inhibitory neurotransmitters are the nervous system's off switches. Excitation in the brain must be balanced with inhibition. The primary inhibitory neurotransmitters are GABA and serotonin. Other neurotransmitters, such as dopamine and acetylcholine, may have both excitatory and inhibitory effects, depending on the function of the binding receptor. Receptor activation may have direct effects on the nerve cell or activate second messengers. Second messengers can then have local or systemic effects. Neurotransmitters can be inactivated and need to be once they're released in order to prevent the nerve from continuously firing. Neurotransmitters can be activated by different mechanisms. The first is diffusion. In diffusion, the neurotransmitter simply drifts out of the synapse so that it can no longer hit the neuron receptors. Reuptake mechanisms are specialized transporters in the cell membrane, and they take back up the entire neurotransmitter intact and store it into a vesicle again to be reused. Inherited variation in transporters can affect neurotransmitter levels and also affect behavior, mood, and attention. They can also affect the risk for neurodegeneration. And the last way to inactivate a neurotransmitter is to degrade it by different enzymes. Enzymes that degrade neurotransmitters also may degrade hormones or toxicants from the environment, so they're very busy multitasking, trying to keep us balanced. The evaluation of neurotransmitter intermediaries can provide a functional assessment of catechol O-methyltransferase and monoamine oxidase enzymes, which are often reported in genetic assessments. A recent article published in The Lancet in 2011 stated that for the neurobiogenic amines, disease onset can occur at any time from infancy onward. The clinical presentation depends on the abnormality in the neurotransmission. That neurotransmitter disorders can mimic other neurological problems and may be misdiagnosed. And the article recommended that clinicians have an early clinical suspicion and apply appropriate investigations, including the analysis of neurotransmitters, in order to accurately diagnose their patients. Now, the Lancet did recommend the conventional medical standard of cerebrospinal fluid testing, but that procedure is extremely costly, very uncomfortable for the patient, which can alter neurotransmitters all by itself. It's stressful. And it's not easily incorporated into most private practices. Fortunately, some neurotransmitters have been correlated with both cerebrospinal fluid and platelet levels. And the one that is correlated the best, serotonin, is actually the one that's the most likely to be different in the central nervous system versus the periphery, because there are two separate isoforms of one of its synthetic enzymes. Now, platelets were most strongly correlated in this particular study. However, other studies have shown that platelets can sometimes have stability issues during collection and transport. Urinary neurotransmitters are much more stable and reliable in their use as a screen or a diagnostic tool. The urinary biogenic amines, or neurotransmitters, provide an overall assessment of a patient's ability to synthesize and metabolize neurotransmitters, which must occur in both the peripheral nervous system and behind the blood-brain barrier in the central nervous system. Altered patterns of urinary neurobiogenic amines may highlight the need for precursor amino acids or nutritional cofactors essential for synthesis and metabolism. The enzymatic machinery for neurotransmitter synthesis and metabolism is often similar, if not identical, on both sides of the blood-brain barrier. Urinary levels of neurotransmitters primarily reflect the activity of the peripheral and gut nervous systems, but up to 20% of some urinary neurotransmitter metabolites may originate from the CNS. Normalizing urinary neurotransmitters has also been shown to result in the improvement of some mood and behavior symptoms, which makes urinary neurotransmitters a valuable clinical tool. Neurotransmitter metabolic pathways are very complicated. The evaluation of the metabolic intermediaries, seen here in orange, helps provide a functional assessment of variably inherited enzymes that may affect neurotransmission, all of which may respond to nutritional interventions. The assessment and correction of nutritional deficiencies is an essential aspect of patient management, but not the only aspect that needs to be addressed. A lifetime of epigenetic exposures, environmental exposures basically, overlaid on individual inheritance may result in neuroinflammation or other neurologic disorders. Neuroinflammation can contribute to behavior and mood issues throughout life, and later in life promote neurodegeneration and cognitive decline. It may be vitally important to assess and correct a variety of variables that may interfere with normal neurotransmission. Unfortunately for us, there are a variety of therapies that may support normal enzyme functions and decrease inflammation. Major mood disorders and cognitive disorders represent a spectrum of brain disorders with multiple etiologies, including genetic vulnerability, environmental stress, dysregulation of neurotransmission, altered neuroplasticity, and altered gene expression. As biological abnormalities are increasingly identified among patients with neuropsychiatric disorders, the distinction between neurological and psychiatric illness begins to fade. The microbiome can actually contribute to some mood and behavior disorders. The microbiome is the collection of bacteria in our gastrointestinal systems, and they may synthesize and release a variety of amino acid neurotransmitter precursors and neurotransmitters or their analogs, such as GABA and acetylcholine, so that the bacteria in the microbiome can participate in crosstalk with our immune system and our central nervous system, and thereby influence mood, behavior, immunity, and inflammation. The ability of bacterial pathogens to influence behavior has been recognized for decades. Increasing evidence indicates that gut microorganisms may directly interact with elements of the host's neurophysiology in ways that ultimately result in modification of the host's behavior. The administration of pro-inflammatory agents, such as the endotoxin lipopolysaccharide, which is a product of bacterial cell walls, can induce the development of depressive symptoms in humans, along with symptoms of sickness behavior. Neuroinflammation of the central nervous system may result if there are high levels of these lipopolysaccharides in the central nervous system or in the circulation. Life in our modern society ensures daily exposure to a variety of neuroactive and neurotoxic substances. There's very little information on the human bioaccumulation of many toxic chemicals and metals. Renewed interest in neurotoxicity began in the 1970s when investigators reported an increased frequency of neuropsychiatric symptoms in industrial workers. The workers experienced reduced vigilance, decreased response times, and memory and cognition changes. Some toxic exposures may occur as the result of lifestyle choices or metabolic errors, and toxic elements such as aluminum, arsenic, cadmium, lead, and mercury are so common in our modern society that acceptable background levels of exposure have been established for many of these. Lead in particular is associated with developmental disorders, cognitive deficits, and behavior problems. Toxic elements may competitively exclude nutrient elements from enzyme interactions. Many enzymes depend on mineral cofactors for proper function, and the replacement of a nutrient mineral element with a toxic element may further inhibit enzyme functions. Nutrient elements in either excess or deficiency may also affect enzyme function and neurotransmission. The interaction of inheritance in the environment, termed epigenetics, is the effects of diet, nutrition, toxic exposures, and stress. And all these factors may help rewrite the genetic expression of DNA without rewriting the genetic code itself. Many types of toxic epigenetic exposures have been associated with changes in behavior and neurological processes in animal studies. Toxic exposures may induce epigenetic changes that can alter enzyme function, exhaust antioxidant reserves, and overwhelm detoxification pathways. A 2015 study demonstrated that the mothers of children with ASD or ADHD had a significantly higher mean chemical intolerance score than did the mothers of controls and mothers of normal children, and that these chemically sensitive mothers were also more likely to report adverse reactions to drugs. Now, the evaluation of a patient always begins with a detailed history, and in our case, we want to include a history of toxic exposures, living conditions, and hobbies. A physical examination rules out metabolic causes of neurological symptoms because neurological disorders can result from metabolic problems as well as dysfunctions in the enzymes of neurotransmission. A neurologic baseline exam provides a baseline to evaluate the effect of any therapies that are then provided to the patient. And while an acute exposure or an obvious exposure history can be easily diagnosed and dealt with, sometimes cumulative or less obvious exposures may be difficult to discern. Sometimes a neurobehavioral assessment can play an important role in the determination of the functional impact of neurotoxic exposures. Neurobehavioral testing, however, may require specialized training. And lastly, we want to use our urinary neurobiogenic amines testing to evaluate the enzymes of neurotransmission to rule out a problem in that system. Now, while pharmaceutical supports may work well for certain individuals, they may not work at all for others or have some unacceptable side effects. And while nutrition is as important to mental health as it is to cardiology, endocrinology, or gastroenterology, in the research and the scientific literature, single nutrient strategies have performed poorly in controlled scientific studies. And there have been very few studies of full nutritional protocols until this study was published in 2014. The study detailed the use of a nutritional protocol to reduce neuroinflammation and improve cognitive function. The study was done in 10 patients with diagnosed cognitive decline, and in 8 of the 10 patients, the cognitive decline was sufficiently slowed to allow them to either continue or resume working. Importantly, the paper emphasized the importance of using only the portions of the protocol necessary, and that would be determined as indicated by laboratory testing. The first step in the protocol addresses the relationship between insulin and brain function. In the first 2 years after diagnosis, it's known that patients with type 2 diabetes may have a decreased ability to regulate blood flow in the brain, and they may have lower scores on cognitive function testing. A metabolomic profile may be used to evaluate the risk of insulin dysregulation in patients, particularly those at risk for metabolic syndrome. And these action steps, as seen on the screen, may be used to improve insulin signaling and blood sugar control. Aerobic exercise has been shown to be important both for blood sugar regulation and also for mood and cognitive health. Recent studies suggest that physical exercise may protect against cognitive decline, although how it improves cognition and mood is still under investigation. A 2003 study found a positive catecholamine response to exercise in children with attention deficit hyperactivity disorder. And a recent animal study demonstrates that exercise can promote increased bacterial diversity, a healthy microbiome, and also improve brain and metabolism in the animal. And another recent study demonstrated that exercise combined with meditation was shown to improve depression in both depressed and non-depressed individuals. The next step in the protocol is to improve gastrointestinal health. The gastrointestinal tract must be functioning normally for nutrients to be digested and assimilated as well. And many detoxification and methylation enzymes do require nutrient cofactors that need to be absorbed in through the gut. We've explored how the gut microbiome can affect neurological function. And psychological stress may act as a toxin and decrease the diversity of beneficial gut bacteria, particularly the Firmicutes phyla shown inside the red circle. In addition, a functional intestinal barrier prevents the translocation of bacterial lipopolysaccharides into the systemic circulation, and reducing those lipopolysaccharides may help reduce inflammation and neuroinflammation. There's been little attention paid to the central role of diet as a variable that influences the gut microbiome, and it's only recent that diet has been associated with mental health as well. Diets that promote inflammation are high in refined starches, sugars, saturated and trans fats, and low in omega-3 fatty acids, natural antioxidants, and fiber from fruits or vegetables, and usually low in whole grains. These Western dietary factors may decrease microbial diversity and increase intestinal barrier permeability, inducing a low-grade systemic inflammation via lipopolysaccharide translocation. In mice, a high-fat Western diet was shown to alter behavior, the microbiome, intestinal permeability, and increase pro-inflammatory cytokine signaling, which in the end resulted in neuroinflammation. The correction of any digestive disorders promotes a healthy, diverse microbiome and also ensures the assimilation of nutrients essential for mental health. Fruits and vegetables provide soluble fiber and act as a natural prebiotic for gut microbiota. Probiotics are a great first step, but they cannot restore full diversity or repopulate the microbiome. Probiotics are transient colonizers and will disappear from the gut about 2 weeks after the last dose. Current research findings do associate nutrition and mental health. Research indicates that the consumption of an energy-dense, high-fat, high-sugar, and sodium-rich diet may increase negative mood 48 hours after consumption. Several recent meta-analyses indicate that diet may modulate mood and behavior and decrease neuroinflammation. And very early animal evidence indicates that a ketogenic diet may modulate NMDA receptor function, which may be useful for some individuals. The next step in the protocol recommends the removal of toxicants, first from the immediate environment to prevent further exposure, and then from the body through the support of detoxification pathways. Exposure to toxic elements and other toxic chemicals increases the amount of oxidative stress in the body, which can further promote neuroinflammation. Urine porphyrins may elevate due to metal or chemical exposures, but may not provide specific indications regarding the toxin causing the elevations if there are overlapping multiple exposures. Screening for exposures with hair, blood, or urine may reveal unexpected sources of exposure, but provides no information about bioaccumulation of the toxins. The assessment of bioaccumulation or net retention of these toxins allows the clinician to monitor the effects of their therapy. Conventional urine or blood results intended to measure true poisoning may look normal during chronic or subacute exposures that can result in bioaccumulation. Therefore, bioaccumulation or net retention is best assessed by provocation and urine toxic elements testing. Metal detoxification strategies may then reduce net bioaccumulation, and evidence of successful detoxification may then be observed on follow-up studies. The next step in the protocol is detoxification to reduce the effects of toxic exposures, which increase oxidative stress. D-glucaric acid indicates recent or ongoing exposure to toxicants and upregulates in response to phase 1 upregulation. Mercapturic acids provide a quantitative measurement of the excretion of conjugated toxins from phase 2. If pathways are healthy, then phase 2 can upregulate to match phase 1. Glutathione, our natural antioxidant, acts as a natural metallothionein. It binds to toxic metals and helps to remove toxic elements and other environmental exposures. A deficient phase 2, as seen here, may indicate a low glutathione level or other problems in phase 2 detoxification pathways such as methylation. The liver detoxifies both metals and organic xenobiotics. Phase 1 detoxification enzymes convert fat-soluble compounds into water-soluble compounds. Toxic metals such as arsenic, cadmium, mercury, and lead may inhibit cytochrome P450 enzymes. Animal studies indicate that lipopolysaccharides released into the circulation may contribute to neuroinflammation in the central nervous system and may then downregulate some cytochrome P450 enzymes through that CNS signaling. Phase 2 detoxification occurs through a variety of different reactions, including glucuronidation, sulfation, methylation, N-acetylation, and conjugation with amino acids or glutathione. Phase 2 conjugations may be inhibited by arsenic, cadmium, lead, mercury, or hexavalent chromium. And we need to remember that there's a third phase to detoxification, as the products of phase 1 and phase 2 must be exported from the cell into circulation for final excretion in the stool or the urine. The next step in the protocol is the functional evaluation of methylation capacity. Now, the protocol recommended looking at only B12 and homocysteine levels. We know that the level of S-adenosyl homocysteine is as important as homocysteine. And we also know that the function of these enzymes may be affected by nutrition, antioxidant status, toxic exposures, basically epigenetics, as well as by inheritance. It's not enough to just look at a genetic profile. Patients require functional assessments of their genetic potential. So the next step in the protocol is actually a functional assessment of the genetics of the transmethylation pathway by looking at the actual enzyme functions. In the first example, poor enzyme function is raising the level of methionine and S-adenosyl homocysteine. When elevated outside the reference value, methionine can be easily oxidized into methionine sulfoxide, which is an oxidative stressor. S-adenosyl homocysteine is also an oxidative stressor and is just as toxic to the body as homocysteine is. In our second example, we see a very low SAMe level and a very high cystathionine level. Low SAMe levels may prevent proper myelination and decrease the synthesis of brain phosphatidylcholine. Low SAMe levels have also been associated with depression and some neurodegenerative diseases. Elevations in cystathionine may occur if there are enzyme deficiencies in cysteine synthesis. Low cysteine levels behind the blood-brain barrier may compromise glutathione synthesis, and a lack of antioxidants in the central nervous system may exacerbate the effects of any additional oxidative stressors and contribute to neuroinflammation or neurodegeneration. So the next step in the protocol is the evaluation of systemic inflammation and oxidative stressors. Chronic and systemic inflammation is believed to contribute to the development of neuroinflammation and neurodegenerative disease. So we would want to check 8-OHDG levels as are measured in the DNA oxidative stress assay to look at DNA damage from increased oxidative stress. And then we would want to look at glutathione levels to evaluate glutathione status and antioxidant status, because glutathione is essential to detoxify toxic metals and promote normal antioxidant status. Antioxidant status may be improved by nutrient supplements in addition to the promotion of glutathione synthesis. The need for specific nutrients such as essential fatty acids may be measured in red blood cells. Mood disorders have been associated with poor essential fatty acid status in some studies. And we need to remember that neurotransmitter synthesis and much of metabolism is an intracellular process. So plasma mineral levels can be transient and not necessarily reflect intracellular status, as they can be easily influenced by daily diet. So the evaluation of elements within erythrocytes provides an estimate of intracellular nutrient status for the last 60 to 120 days. The next step in the protocol supports mitochondrial function. Mitochondrial function behind the blood-brain barrier is essential for normal neurotransmission and metabolism. And we need to remember that magnesium is an essential cofactor for mitochondrial function and neurotransmission. Intracellular magnesium evaluations provide the best estimate of nutritional status. The next step in the protocol is the normalization of hormone levels. Sleep apnea is a common cause of neurotransmitter disruption, so normalizing sleep hygiene is another important piece to the puzzle. In addition, normalizing vitamin D levels may improve inflammation and immune functions. Now, the last step in the protocol from the article is specific for cognitive decline and recommends B5 to support acetylcholine synthesis. We would recommend the additional step of evaluating urinary neurobiogenic amines to provide a functional baseline that can then be used to monitor the efficacy of all these therapeutic interventions. And in addition, some non-nutrient therapies might be considered by the clinician. Chronic psychological stress may also be disruptive to neurotransmission, while evidence-based mind-body therapies may improve stress, cortisol, and catecholamine levels. Both PTSD and low socioeconomic status have been associated with an increased prevalence of mood disorders in children and adults. And evidence-based mind-body therapies may improve stress levels, cortisol, and catecholamine levels. A 2016 study demonstrated that the combination of meditation and exercise decreased depression 40% in depressed and non-depressed students. We also need to remember that our circadian rhythms regulate the homeostasis of oxidative stress, as well as neurotransmission and a variety of other important metabolic functions. The primary circadian clock is located in the hypothalamus, where light signals from the retina, endogenous hormones, and neurotransmitters, as well as environmental stimuli, converge to reset the phase of the circadian clock. Circadian rhythm disruption may be a biological stressor that interacts with Western dietary habits to promote increased intestinal permeability and the loss of normal microbiome diversity, and may also contribute to increased inflammation. Sleep apnea can also alter urinary neurotransmitters, and cognitive impairments have been linked to sleep apnea. Blue light from the screens of phones and tablets may disrupt melatonin synthesis, and according to research by the University of Pittsburgh, the more time young adults use social media, the more likely they are to be depressed. Further evidence indicates that night shift workers may be at risk of altered neurotransmission and decreased fertility. So I'd like to move on to a case study. Our patient today is a 10-year-old male diagnosed with attention deficit hyperactivity disorder. Stimulants were tried but not tolerated and worsened the child's symptoms. The parents are seeking an alternative. The patient currently lives in Hong Kong. The first morning void results show some out-of-range findings. The first thing we see is that the enzyme that converts dopamine into norepinephrine is not doing so with any efficiency. Now, the enzyme that converts dopamine into norepinephrine requires two cofactors, copper and vitamin C. The conversion of norepinephrine to epinephrine, which is seen here, is equally poor and is a SAMe-dependent process. Of interest, histamine levels are fairly high, and they are also dependent on copper and SAMe to metabolize and degrade the histamine. So we're seeing a very clear pattern here of some nutritional needs in this child. This finding, plus a low taurine level, indicates the need to check the transmethylation status. In addition, high levels of trace amines can act like stimulants and may be the reason that the stimulant medications were not tolerated by this particular patient. And then lastly, unless this is the result of direct supplementation, high tyrosine levels indicate either a liver disorder or an inherited variation in the enzyme tyrosine aminotransferase found in the liver. Tyrosine aminotransferase is meant to control blood levels of tyrosine to prevent the excess synthesis of dopamine. And if this enzyme is dysregulated, high tyrosine levels in the urine are seen, and excess dopamine may be synthesized, which may further exacerbate problems. We were lucky enough to get some additional testing on this patient. We got a stool analysis, and we begin to see the beginning of a stress pattern. The Firmicutes phyla species are starting to drop off. A loss of lactobacillus diversity, should it continue, can further affect mood and behavior. And lactobacillus is also very important for the removal of toxic metals. The bacteria sequester metals in their cell walls and are then excreted in the stool. In addition, the patient has a 2+ candida overgrowth, and the candida overgrowth can contribute to food allergy reactions, which may be contributing again to that higher histamine level. We often see higher histamine levels in patients on standard diets, and we see improvement in those levels on oligoantigenic diets. The rest of this particular stool analysis was unremarkable. We were lucky enough to get an unprovoked urine toxic elements and did find a significant amount of recent arsenic exposure. Unprovoked urine toxic elements reflect 1 to 2 weeks of exposure, so this is a fairly recent significant finding. The patient has had a significant ingestion of arsenic, and if this is chronic, arsenic can alter learning, memory, and cognition in children and may make a modest contribution to ADHD symptoms. Arsenic can also affect transporter systems for dopamine, serotonin, and norepinephrine, may prevent reuptake back into the neuron, which would further dysregulate neurotransmitter levels. And in addition, arsenic is a major biological antagonist to selenium, which is required for normal monoamine oxidase function and neurotransmission. We were also lucky enough to get a plasma methylation profile on the patient, and in this particular patient, we see that methionine is not converting to SAMe efficiently, which can be due either to a magnesium deficiency, oxidative stress, or genetic variation in the enzyme. We also see that cystathionine is not converting to cysteine efficiently, and while this transaction in the periphery can be bypassed by dietary cysteine in circulation, an inability to synthesize cysteine and glutathione behind the blood-brain barrier contributes to neuroinflammation, oxidative stress, and disruptions in neurotransmission. So for this particular patient, we would want to decrease phenylalanine and tyrosine intakes and artificial sweeteners that may break down into phenylalanine in order to try and lower those tyrosine levels and ameliorate the high dopamine levels and some of the symptoms. We would want to avoid histamine and trace amines in the diet, again, to try and minimize those exposures and normalize the patient's responses. Another thing that might be tried involves the support of monoamine oxidase with forskolin, because that may increase the breakdown of these trace amines. And then lastly, we would want to increase vegetable intake, and we would want to encourage quiet, mindful, distraction-free meal times for this child to try and improve parasympathetic tone and signaling and restore the microbiome. So further supports for this patient would include forskolin, as mentioned, which in vitro has been shown to increase monoamine oxidase expression. MAOA is one of the primary enzymes to break down catecholamine neurotransmitters, and it's also important in the gut to break down trace amines. We would want to assess nutrient element levels in red blood cell elements profile, and then supplement any minerals that were found to be deficient to further support normal enzyme functions. We would want to supply vitamin C, which is an essential cofactor to convert dopamine to norepinephrine. And as indicated by testing, we would want to provide nutrient supports for the enzymes of the transmethylation pathway. Heme is an essential cofactor for the conversion of cystathionine into cysteine. So we would want to evaluate urine porphyrins, which look at the enzymes of the heme synthesis pathway. And as discussed, that pathway can be disrupted by toxic exposures. We would also want to further evaluate hepatic functions, including genetic testing for tyrosine aminotransferase, if indicated, And we would want to look at the hepatic detox profile as well and further support phase 1 and phase 2 functions as needed. Arsenic is known to contribute to liver inflammation and fibrosis, and the elimination of the arsenic exposures and the pursuit of metal detoxification therapies may improve enzyme functions and decrease oxidative stress. In addition, the clinician may consider some non-nutrient therapies, such as time outdoors in nature to improve vitamin D status, and exercise, which has been shown to improve catecholamine levels in ADHD boys, and in a separate study was shown to improve behavior, cognition, and scholastic performance in ADHD patients. So we've reviewed the evaluation of biogenic amines and neurotransmitters and the effects of dysfunction in synthesis or metabolism. We've reviewed how environmental exposures and inheritance may affect enzyme functions and neurotransmission, and we've reviewed strategies for nutritional support of neurotransmitter synthesis and metabolism as outlined in the scientific literature. And we've looked at a few strategies to help clinicians diminish oxidative stress and neuroinflammation in their patients and hopefully correct neurotransmission and enzyme function so that their patients can lead healthy, normal lives. I thank you for your kind attention, and we'll take questions now.